Welcome to AP Physics 2. This is a review series for the AP Physics 2 exam. And it does assume you know AP Physics 1, things like forces, kinematics, work, things like that. And you might want to have a solid background in AP Physics 2 before watching this, because this is mostly a review series, so I'll go through the content pretty quickly and then do two MCQ practice questions and one FRQ practice question to review what we just covered. So this is theoretically supposed to be just preparing for the exam, not like a complete overview of AP Physics 2. And it's going to be broken down by different units. So this first video is Unit 1, Fluids. And here is the list of all the equations on the AP Physics 2 equation sheet that relate to fluids. And you might know none of them right now, you might know all of them, and you might know just some of them. But that doesn't matter. We're going to be going through all of these equations and even more, some that don't appear on the equation sheet, soon enough. So without further ado, let's get started with Unit 1. Okay, first of all, what is a fluid? That's the name of this unit. We need to know what that is. A fluid is either a liquid or a gas. Generally, when we think of fluids, we think of liquids, but it can also be a gas. The definition of a fluid is that it can flow and it has pressure. And don't worry, we'll get to pressure soon. You don't need to know that just yet. But that's just the definition of a fluid you might want to know. Liquid, you might have learned in a previous science class, just takes the shape of its container, meaning it has a constant mass and constant volume. You can't change it. And that's what we call incompressible, because you can't change the volume. On the other hand, gas doesn't just take the shape of the container, it completely fills it. It expands until it reaches the ends of the container. And that's why, while it does have a constant mass, its volume does change. And that's what we call compressible, because you can change its volume. So that's the main difference between them. And with that contextual background, we're ready to get started with the actual equations and formulas and things like that. First of all, the first quantity we need to know is density. Density, which has this Greek symbol rho, is the mass per space occupied. And that's going to be m over v. V is volume, m is mass, or rho is density. And similar quantity, similar symbol, so you might get confused, pressure. Pressure is going to be force over area. You might know forces from AP Physics 1 is just a push or pull. Now, when you apply such a force over an area, we get a pressure on that area. So when you have a smaller area, it's going to be a larger pressure if it's the same force. There are different types of pressure. First, let's say I'm just standing here on ground. There's going to be some amount of air above me that's constantly exerting some pressure on my head. That's going to be called atmospheric pressure, and that's going to be approximately 101,325 pascals, where Pascal is the unit for pressure. This is also conveniently 1 atmosphere, but we usually use pascals because it's an SI unit that we just use. Now, you don't need to know this exact number. You just need to know it's about 100,000 pascals. That's atmospheric pressure. There's also something called gauge pressure. And that's when you're in a fluid and the pressure exerted by the fluid at a certain depth. So let's say this person's standing here, but there's the beach over here. And so someone is swimming underneath here. Let's say there's some distance h below the surface. Not only do they have the atmospheric pressure pressing down on the water, they also have the water pressing down on them. And this water pressing down on them is called the gauge pressure, and it's equal to the density of the fluid times g, the gravitational constant, times h, the amount of fluid above them, rho gh. And their total pressure then, their absolute pressure is what we call it, is equal to the atmospheric pressure plus the gauge pressure above them. You might want to know this, but pressure is basically caused by the sum of many microscopic collisions. So just atoms and molecules colliding with each other, causing a net force in one direction, which ultimately causes the pressure in a container. So Pascal's principle is pretty important when dealing with pressure. Basically says that the pressure at all at all points at the same height in a incompressible fluid is the same. So this person swimming here, this person swimming at the same height, they have the same not only gauge pressure, but also absolute pressure, because that's always constant no matter where you are. Then the gauge pressure is also constant depending on the height. So the equation for Pascal's principle basically says that rho 1 h1 is equal to rho 2 h2 Also, force 1 over area 1 is equal to force 2 over area 2. These just come from the definition of P1 equals P2, or the pressures are the same. But you can just write in terms of other variables. And this is important when we're considering things like barometers that have two different areas. So this has a smaller area, this has a larger area. So to keep the same amount of pressure, this must have a smaller force and this a larger force. So you can manipulate the amount of force in some area by just changing the area. Now that we have that, let's try to find out how we can solve some problems with this. So you might know free body diagrams from AP Physics 1. We're going to be using those again, but this time for fluids. And usually what you're going to have is a gravitational force. And there's going to be one new force this time, something called a buoyant force. And a buoyant force is just a force due to a pressure difference, denoted with F sub B. Archimedes' principle tells us a formula for buoyant force is just FB is equal to rho times the volume times G. This is where things get a bit confusing. Well, if rho is just mass over volume, when you multiply by volume to both sides, you get rho V is equal to M. So is this just equal to mg? Does that mean buoyant force is always going to be equal to the gravitational force? Unfortunately, no. Life's not that simple. Well, you could say fortunately, because then we wouldn't have fluid statics and dynamics to work with. But this M in the gravitational force equation is equal to the mass of the object. So if you have a rubber ducky floating here, the gravitational force requires the mass of the object. The buoyant force, though, is what's called the mass of the displaced fluid. And that is pretty different, because if you have something that weighs heavier than the displaced fluid, your gravitational force is going to be higher. When you have something that weighs lighter than the displaced fluid, then the gravitational force would be less than the buoyant force. And this is where we get things that float versus sink. Something sinks when its density is greater than that of the fluid it's in. So if you have like a ball of steel, it's going to sink. If you have a rubber ducky, its density is less than that of the water and it's going to float. So this rho is the density of the fluid, and since the volume is the same, since an object takes up the same volume that it displaces, which also Archimedes proved, this is going to be the mass of the displaced fluid, not the mass of the object. Here, on the other hand, is going to be the mass of the object. So always be careful of that. Usually, your buoyant force is going to be different from your gravitational force. If your buoyant force is higher, that means density of the object is going to be lower, and so it floats. And you can do the same thing for when an object sinks. Okay, this is what we do in fluid statics. Things really don't move. The buoyant force does make objects move, but we don't really consider it moving. We just consider it to be at an instant in time. This is what the forces acting on it are. Then we have fluid dynamics, which is when things actually move. You might remember energy from AP Physics 1. We're going to be coming back to that, specifically conservation of energy. And that says that the total mechanical energy of a system is constant. Bernoulli's equation is pretty important for this, because it is basically the embodiment of conservation of energy in fluid flow. And it's a pretty long equation. It is on the equation sheet. It says P1 plus rho G Y1 plus 1/2 rho V1 squared is equal to P2 plus rho G Y2 plus 1/2 rho V2 squared. Okay, what in the world is that? First, that's the pressure at two different points. This is the gravitational potential energy. You might remember that's mgh, but it's a bit weird. Why is there a rho there? We'll get to that in a second. There's also this, which looks a lot like 1/2 mv squared. What's going on here? Well, the thing is, you're basically just getting it from conservation of energy, because this appears in conservation of energy. You know that the sum of potential and kinetic energy have to be constant. Now you're just dividing by volume to make things related to fluids with density involved. And it's more complicated than that. You're not just dividing by volume just to make it look more complicated. There's a reason why, and it has to do with the pressure term here. You don't really need to know how to derive it, you just need to know how to use it. At two different points in a fluid, let's say this one, this is going to be constant. The velocity at that point, it follows this rule. The pressure at that point follows this rule, and so on. You do need to know this, but it is on your equation sheet. And so an interesting consequence of this is called Torricelli's theorem. This is not on the equation sheet, but it says if you have just a hole in the fluid and it's squirting liquid out, it's a height h below the surface of the water, not h above the ground, but below the surface of the water. The velocity of the liquid squirting out is going to be equal to square root of 2gh. You cannot just memorize this. You have to derive it on the equation, on the test, if you want to use it. If it's an FRQ. If it's an MCQ, by all means use it. They're not going to check your work. But if it's an FRQ, you need to know how to derive from Bernoulli's equation. And I will show you how to do that later in the video. No, I'm kind of spoiling the FRQ later on, but we're going to be doing this. So that's conservation of energy. You need this equation. It's very important. But what about conservation of mass? Conservation of mass basically says that mass is constant in a system. But we're going to expand that into something called fluid flow rate or volumetric flow rate. And that's given the symbol Q. It's basically equal to the volume over time. And since we know mass is always constant in any fluid, we basically just expand that conservation of mass to conservation of fluid flow rate. So one thing you might notice here, volume, this is volume, not velocity, over time. Well, volume is just area times the amount you're moving it. Because if you have like a cross-sectional area and you're just moving it, then you get a volume. So that delta x is how much you're moving it over time. Well, that's just area times delta x over time is velocity. So area times velocity. So this is another equation for volumetric flow rate. Now, the continuity equation is another really important equation you need to know. It says that the volumetric flow rate is the same throughout, which basically says that A1 V1 is equal to A2 V2. And here V is velocity, not volume. This is also on the equation sheet, so no need to memorize it, but you do need to know how to use it. So if you have a tube where the volume is the area, the cross-sectional area is changing, then the velocity is also changing similarly. That's the important stuff of Unit 1. There's some niche topics like the Venturi effect that I'm not getting into, but it's barely covered in the AP exam. And if it is, you would know how to answer those questions using what we learned. So, time to move on to the MCQ practice. Here's our first question. It basically says that there's a cylinder and there's a lid on top. This has a pressure of 10,000 pascals. Now the outside has a atmospheric pressure of, let's just say 100,000 pascals. No need to remember the exact value. We know that the radius is 5 centimeters, the mass is 400 grams. Let's convert that to SI or base units. 5 centimeters is 0.05 meters. Mass is 400 grams, which is just 0.4 kilograms. And let's see. We want to know if the lid pops off or if it remains sealed, which sounds like a force problem. If the forces upwards are greater, then the lid pops off. So let's try drawing a free body diagram. We know there's the gravitational force of the lid. We also know that there's a pressure difference here, meaning there's also going to be a downwards force due to pressure. So I'm just going to call that FP. Now there's the upwards force that you're just applying 800 newtons, so FA for applied force. We want to see if FA is greater than the sum of these two forces. So how can we do that? Well, let's start with the gravitational force. That's easy. It's just mg. We know m is 0.4. We can just use g is 10. They allow us to do that on the AP exam just for easier calculations. So 0.4 times 10 is 4 newtons. Not that much, especially compared to the 800 newtons that is the upwards force. Let's try the pressure force though. The force due to the pressure difference. Well, what is the pressure difference? That's 100,000 minus 10,000, which is 90,000 pascals. And we know that pressure is equal to force over area. So, multiplying both sides, force is 90,000 times the area. And what's the area of a circle? That's just pi r squared. So 90,000 times pi times the radius 0.05 squared. You just plug that into a calculator. You get approximately 706 newtons. 706, 707, depending on how you're rounding it. But either way, we see that the sum of this, which is 710 to 711, depending on how you round it, is always going to be less than the applied force 800. So it does pop off, meaning we can get rid of the answer choice D. But how much does it accelerate upwards? Well, if we just subtract the forces, we're going to get around 90 newtons divided by the, we know force is equal to mass times area, mass times acceleration, sorry. And we know this net force is around 90 newtons, mass is 0.4, we solve for area. Does that give us our answer? The answer is no. And this is probably why this question is pretty tricky, and that's why I wanted to go over it. It doesn't give us our answer. And the one thing wrong with that is because once the lid pops off, the instant it pops off, it says, and then accelerates upwards. So we're talking about after it pops off. There's no more pressure difference. The instant it pops off, it automatically turns to atmospheric pressure because it is in contact with the atmosphere now. There's no more pressure difference. And so the only net force is the applied force and the gravitational force, and so 796 newtons. And that's equal to mass times acceleration. So always be careful of how your free body diagram changes over time. Now to calculate your answer, you just do 796 over 0.4. That's going to give you 1990 meters per second squared for the acceleration. That's around 2000, so we can say our answer is A. Yeah, so just be careful of things like that. They might try to confuse you. But moving on to our second question. Again, pause if you need to try to solve it yourself. This one is a conceptual question mostly. This is just our continuity equation because it's talking about volumetric flow rate. So, and velocity. We know that volumetric flow rate is Q, and that's equal to AV. First of all, you immediately think the continuity equation. It does say that A1 V1 is equal to A2 V2, but what else does it say? It just says that Q1 is equal to Q2. That is basically what it says. It's constant no matter what. And if you pay close attention, if the flow rate is Q here, it must also be Q here. And so the volumetric flow rate must be Q, and our answer is C. But that isn't really that fun of a problem then if we don't have to do anything. So let's just double check our answer by calculating the linear velocity. We know the area is proportional to the diameter squared. It's actually proportional to the radius squared, but the diameter is proportional to the radius. So we can just say the area is proportional to the diameter squared. And this diameter is D1, that's D2, which is 1/3. So the area here is proportional to 1/3 of this diameter squared, which is 1/9 of the diameter squared. And so this area 2 is equal to 1/9 of area 1. And so if we plug that back into this equation, we see that area 1 times V1 is equal to 1/9 of area 1 times what times V1? What factor multiplied by V1? Well, it just has to be 9 to cancel with this 1/9, which means that the velocity must be 9V. That does agree with our previous choice. So just double checking your work. This problem really shouldn't take that long because it's just pretty simple. The volumetric flow rate must be constant. And finally, our FRQ practice problem. This one would take a bit longer, so let's chug along through it. Okay, this is just the Torricelli's theorem if you read through it. It's a cylinder with water in it. Water is flowing out of a hole. That's just Torricelli's theorem. And so our answer to A, it says, what speed does the water emerge from the hole? That's exactly what Torricelli's theorem tells us. V is equal to square root of 2gh. Is that our answer, though? It is our answer, but it's not our solution. We need to derive it. Like I said, it's not on the equation sheet, meaning you have to derive it. So we can't just write this and expect our grader to just accept it. We need to show that we know how to derive it. Let's start with Bernoulli's equation. P1 plus rho g y1 plus 1/2 rho v1 squared is equal to P2 plus rho g y2 plus 1/2 rho v2 squared. Okay, looks complicated. Don't worry though. Let's say point 1 is somewhere on the surface of this water. It doesn't matter where, because Pascal's principle tells us that the pressure is going to be the same everywhere. P2 is going to be the hole right here. And we have to use those for our 2 points. First of all, it says at the top the speed with which the water level drops is negligible. So, this is 0 because the velocity at the top is 0. Another thing to note, there's these two pressures. You might be thinking, well, this is just atmospheric pressure, which is true. And this one is the absolute pressure, which is the atmospheric pressure plus the gauge pressure. And we know gauge pressure is rho gh, so we can plug that in. If you do that and simplify, you're going to get that velocity 0. And you might just be confused and then give up on the question and move on, which is a perfectly valid method if you are confused. But this, like the first MCQ problem we did, is a bit tricky. If there was no hole, if this point was just here, then you, by all means, calculate this and you get the velocity 0. The velocity is not changing at some point if the hole is not there. But the hole is there, and there is some velocity. So what does that mean? Well, like I said, the instant the hole is there and the instant the water moves out of the hole, there's no more pressure difference, meaning it's in contact with the atmosphere, and so the pressure at that point is the atmospheric pressure. It's just the atmospheric pressure. It seems counterintuitive, but it's true. As soon as it reaches the atmosphere, it's atmospheric pressure. No matter what other point here, no matter the pressure elsewhere here, it's going to be the atmospheric pressure as soon as it touches the atmosphere. And so these cancel off. Now it looks a bit more manageable. We have rho gy1 is equal to rho gy2 plus 1/2 rho v2 squared. Okay, let's cancel off a rho. We have gy1 is equal to gy2 plus 1/2 v2 squared. Let's move the gy's to this side. We have gy1 minus gy2 is equal to 1/2 v2 squared. And so multiplying by 2, we get v2 squared is equal to 2 times g. We can actually factor out a g times y1 minus y2. And v2 is equal to the square root of 2g times y1 minus y2. Almost there. It's just we don't have a y1 or y2 given in this problem. And if you notice, the y1 minus y2 is just the change in height, and that's going to be h. So v2 is equal to square root of 2gh. And that would be your answer. We just proved Torricelli's theorem right here on the AP exam. That's what you're going to be expected to do, actually. So be prepared to do that. And we can even remove the subscript 2 because they didn't specify that it's the second point. So that's going to be our answer. Okay, now usually the problems get harder as you move on, A, B, C, D. But in this case, it actually gets easier. I'll show you why in a second. How far is point X from the edge of the tank? Well, we found the velocity here. Is this just kinematics? And it is. Surprisingly, A is the only question that relates to AP Physics 2. We didn't get to C yet, but it also, you can solve without knowing AP Physics 2. B is just AP Physics 1 kinematics. We know for projectile motion, delta x is equal to VIX times delta t, and delta y is equal to VIY times delta t plus 1/2 g delta t squared. And you can consider it to be plus g or minus g depending on if you say g is positive. Usually I like to say g is positive, so I would just put a minus here. And these are given on your equation sheet, so you can just use them. Now, what do we do from here? Well, we're going to have to use both equations, unfortunately. We don't know time. And so we can just plug it into this equation. Here, we know delta y is just going to be d minus h, because d is the total height, that's h, so it's just d minus h above the ground. It's actually going to be negative of that because you're going down towards the ground, so it's a negative vertical displacement, and it'll be pretty important in the future, so just write that for now. We know this is 0 because when you're just shooting out of a hole, there's no initial vertical velocity. It's like horizontal projectile motion. So it's just equal to negative 1/2 g delta t squared, and so d minus h is equal to 1/2 g delta t squared. That's why we had to put that negative so that the negatives cancel and we actually get a reasonable answer. Multiply by 2 and divide by g, you get 2 times d minus h over g is equal to delta t squared. And so delta t is equal to square root of 2 times d minus h over g. Now we can finally plug this back into our first equation. We have delta x, which is what we want to find, is equal to VIX, which we said was square root of 2gh, times the square root of 2d minus h over g. And we have two square roots, we can combine them. We can actually take the 2 out because 2 times 2 is 4, and square root of 4 is 2. So 2 square root, these two g's cancel off, and all we have left is this h times d minus h. And that's going to be your answer. Delta x is equal to 2 times the square root of h times d minus h. See, no AP Physics 2 required, just AP Physics 1. Unfortunately, though, you do need AP Physics 2 because A depended on AP Physics 2, and so you can't really solve B without A. You do use the velocity. So that's a bit tough. Now, what about C? It looks complicated. Assume that a second hole is punctured in the side of the tank. H over 2 above the hole shown. So that means this is H over 2, and as is this is H over 2. If the stream also lands at point X, find H in terms of D. That seems counterintuitive. How can it land at the same point? Well, let's try using math to figure it out. We know delta x has to be the same. This is just a general equation because we didn't plug in any numbers. We just plugged in h. So we can just replace h with h over 2 since that's the distance from the surface. So let's plug that in. I'm just going to write 8 sub h over 2 to say that this is the h over 2 displacement. And that's equal to 2 times the square root of h over 2 times d minus h over 2. D is constant. Delta x h is equal to 2 root h times d minus h. And we know these are equal because that's what it tells us. So the 2's cancel. We can square both sides to get rid of the square root. And we have h over 2 times d minus h over 2 is equal to h times d minus h. We know h can be 0 because you can't just have a hole at the surface. So we can divide by h here. And we get 1/2 times d minus h over 2 is equal to d minus h. And multiplying by 2 to get rid of the fraction, d minus h over 2 is equal to 2d minus 2h. And so moving the d to this side and the h's to that side, we have 3/2 h is equal to d. And we want h in terms of d. So actually h is equal to 2/3 d. That would be our answer for part C. Does that make sense? Well, if this is just 2/3 of the entire distance, this is 1/3 of the entire distance. And so it kind of makes sense that, well, this one's 2/3 from the top, this one's 2/3 from the bottom. Maybe something like that's going on. If you try it at home, it actually does work out. Our math isn't wrong. So like I said, A is the only one that requires AP Physics 2, fluid specifically. B does not. C does not. C is just pure math. There's no physics required even. So yeah, there actually is a part D to this, but I didn't include it for the sake of time. You can search up this problem and find the part D if you really want to. But yeah. And that wraps it up for our first video for fluids. Keep a lookout for the second video, which is about thermodynamics. And as always, leave a comment down below if you have any feedback. If you want more time spent on content, more time spent on the practice, just let me know. And yeah, so good luck for the AP Physics 2 exam. See you next time.